Professor Coles. I'm just going to go over summarize our lecture on the Kelvin wake, because I was forced to go through things a little quickly, having spent so much time on the homework. Let me see if I can blow this window up. There we go. Alright, I'm just going to go over the key points that I want you to know. The key, starting off with these waves. In general, we have ships making waves. Here's the Kelvin wake you can see up here. So the ship's transferring energy to the waves, and for a lot of the ships we'll study in this class, most hull forms, when they reach their sort of operating speed, a large fraction of, a significant fraction of the energy is being lost to this wave train. These, of course, surface-piercing ships as opposed to submarines. So it's important to quantify the development of those waves and how much power is being lost to push them. Now, as we mentioned before, we sort of divide it into a wave problem and a skin friction problem. The skin friction is easier to estimate. So essentially what we do in the wave tank is maintain the same Froude number, and I hope I can convince you, or have convinced you, that in fact the wave train is connected with the Froude number. So we keep the same Froude number and have a geometrically similar, similar wave train, estimate the wave drag coefficient on the model, and then, or measure the wave drag coefficient on the model, estimate friction drag using formula, and that'll allow us to scale up the total drag. We'll see the process in more detail after the break, up to the full-scale model. Now if we look at wave drag, this is a simulation, but this you would see this in a tow tank test as well. But in the simulation you can actually cut apart wave and frictional resistance. So here we have frictional resistance, which is this red curve here, which is sort of essentially goes up quadratically with the velocity. That's not exactly true because the wave drag coefficient is, the friction drag is dropping, so it's not quite quadratically. And we have an estimate of the wave drag here, and this is computed by, I just basically solve what's called a Michel integral. Gives you an estimate of the wave drag. It has some assumptions which make it not work for large waves, boats with big beam, those sort of things. But for this ship here, this is reasonable. And you see the wave drag, which is this blue line. Wave drag oscillates. There's a trough here, a peak here, a trough here, a peak here. It comes up to a large peak here at about a Froude number of 0.6. Now this is a pretty typical looking curve. We have our last peak somewhere between 0.3 and 0.4, last trough, and then you have a very rapid drag rise. At very low speeds, friction dominates. At larger speeds, the wave drag dominates. And it's right around here that we basically assign a rough barrier to the top speed of a displacement vessel, because at that point the incremental power needed to get a higher speed is so great that it's not economically efficient. To get past that barrier, and it isn't a hard number, but it's right around Froude number 0.4 is an approximate back of the envelope calculation, and that corresponds to a speed to length ratio of about 1.3. To get past that, you have to have a hull form that can overcome this large drag rise by either hydrodynamic forces to lift it out of the water, that's a planing boat, or using foils, for example, to lift the hull out of the water. So you have to reduce the displacement to reduce the wave making and get this curve. The curve will continue to increase, but not at such a slope. We'll study those two types of boats later in the class. So what causes these oscillations? They're unusual in the resistance world. Most often we just see forces on a body just simply increase monotonically with increasing speed. That can be lift or drag, or torques, moments. In this case, it goes through this regular oscillation. So what causes those? And those are really what helped Froude to come up with his early model testing procedure, where he discovered if he lined up the full-scale resistance and the model resistance, and on the x-axis he used the speed-to-length ratio, it caused these humps and hollows to line up. They were aligned in terms of V over root L, and he realized that was the critical parameter for model testing in order to have wave similarity between model and full scale, and that's really what enabled model testing to work in the first place. We now call that the Froude number, but in his time he used V over root L, which again is not non-dimensional, has strange units, but they're essentially the same parameter. So I won't go through all the slides because I did go through them in lecture. I do encourage you, if you have time, to click on this link here. Ernie Tuck's work is beautiful work, computing wave integrals to look at the wave field. And there are, again, some assumptions in that theory, viscid and thin chip and such, but for the hull forms he studied, they're quite exquisite. And he does some interesting work where he tries to get waves to cancel out. And this is analogous, if you're familiar with supersonic flow, to the Boostman biplane. Essentially, if you have two objects generating wave trains, you can align them at a given speed in such a way that they can partially cancel out the waves. And so he did that. It was theoretical work. It's quite interesting. So Lord Kelvin was the first one to really describe this idea of a wake. So if we come back, I'm just going to come back for a second, and you can see it in these images. There's a RANS computation. This is Tuck's work, which is an open source code, and you see here the complexity of the wave train. You see these sort of swathing waves back like this, and it's hard to see in here, but there's also a wave sort of following the boat like this, and right along the boat generated here. So there are two types of waves, and we're going to distinguish those wave trains as transverse and divergent waves. The divergent waves are these swoopy waves out here, and they live within an envelope of 19.47 degrees, and that is not dependent on the speed. That is a fixed number as long as the ship is operating in deep water. And then we have these other wave trains here, the transverse waves, which are moving along the center line of the boat here, normal to along the ship direction. And this transverse wavelength, we'll go through this formula in a few slides, is related to the square of the ship speed. So the wavelength, or the distance between those transverse waves, is set by the ship speed. Kelvin was the first person to come up with a solution. I've put a link up on my courses with a little more information about his method of stationary phase. The Newman book in the library I put on reserve. He goes through the entire solution, following what Kelvin did, basically taking a moving pressure source and the deep water dispersal wave relation to develop the solution for this wave train. And from there you can actually calculate the wave drag by looking at the energy fluxes across any of these planes here. And Newman's book does that in 2D in a very interesting way, something I had never seen before, and then in 3D as well. It's a lot of math. But the main thing is he was able to describe this fundamental wave system for the first time. It's quite interesting. And the reason for this complexity comes down to the dispersive nature of these water waves, the fact that there's a connection between the wavelength and wave speed, and that's a deep water constraint. We're assuming these ship waves are deep water waves, meaning that their wavelengths that the water is deeper than half their wavelength. Some pictures of Kelvin waves you can see. Each of these items is producing a Kelvin wake, a duck, a frigate, a synthetic aperture radar image of a Kelvin wake of some ship moving somewhere. You can clearly distinguish in there the transverse waves. It's actually a beautiful image. And of course there are a lot of studies, and I asked you to do this in your homework, of processing an image like that to determine the ship speed. And other people were trying to take that to another step to understand if you could really characterize that wake, you might be able to identify what exact ship that is. Now I think that satellite photography has gotten to the point where maybe that's less necessary, but you can get a night image which has an infrared signature, and if you know something about the stratification, because the wake also induces surface signatures in the form of heat, because it may be churning up colder water which is displacing the warmer water in the surface, and perhaps with an infrared night signature you can look at some characteristics of a ship, where it's moving, how fast it's moving, and maybe what type of ship it is. So there was some efforts by the Navy to do that at some point. And you can see very clearly in the sailboat photograph, if you look carefully, the transverse waves. Was one right behind the boat. Here's the next wave crest, here's the next wave crest, here's the next wave crest behind that sailboat. And so the distance between them, I'm looking now, is roughly the waterline length, so that boat's moving near hull speed. The duck's producing a very similar wake to the ship, even though the scale difference is considerable. A duck is about a third of a meter, and the ship over here is probably 200 meters, so the two very different items, provided they're moving at the same Froude number, are going to produce similar wakes. That's the idea. So the waves travel with the ship, so that's the key thing. If you stand on a ship and you look out and you keep your eye on one part of the wake, it appears to be traveling with you because it is traveling with you. So the wave speed is the same as the ship speed, and we're going to focus on the transverse wavelength. So again, the transverse waves are these waves here, and if you want to look at them in here, I think they're most evident in the red lines I put behind the sailboat. The other ones are a little more difficult to see, although you can clearly see them in the SAR photograph too. And so this is the first thing, that the waves travel the ship. So U ship must be equal to C wave, and C wave from our water waves lecture is equal to G lambda over 2 pi, the square root of that. So it's proportional to the square root of the wavelength. That's because deep water waves are dispersive. From that, we can calculate a relationship between the transverse wavelength and the ship speed. It goes as the square of the ship speed. And if we want to non-dimensionalize this for a similarity relation, we have the ratio of the wavelength to the ship length goes as the Froude number squared. So that comes back to this concept that we can look at a duck and a boat, and if we look at their waves, the wave train that they're making, in particular the transverse waves, and the ratio of that transverse wavelength to their size, which are very different, but that ratio will be the same if they are operating at the same Froude number. So this is the key non-dimensional relation here. So this tells us something about the size of this wave. If we think about a wave that's generated at the bow, and the bow is a pressure source, it's going to generate a positive wave train that will extend sternward from the bow. The length of that wave from crest to crest is going to be set up, relative to the boat length, is going to be established purely by the Froude number. Excuse me. So if we want lambda over L to be 1, which it is in this drawing roughly, the wavelength is the same as the boat length, just about. We can solve for the Froude number. That's that magical Froude number, about 0.4. What if the wavelength is 1 crest and then a half? So we have 1.5 wavelengths. So lambda over L equals 2/3, or you can think of it as 1.5 lambda equals L. So lambda over L is 2/3. Solve again for Froude number using this relation up here, and we have a slower Froude number. So you go slower, the transverse wavelength is shrinking. You have more waves along the boat. But we have two examples here, 1 exact wave and 1.5 exact waves, and the corresponding Froude numbers. Now, that's there's one complication, not only complication, but something to consider, and that the bow wave is typically created a bit aft of the bow, and same with the stern wave. And what we're going to do is look at a simple interaction of a bow and a stern wave. Now, the ship is made up of an infinite number of wave trains. Essentially, the boat is sort of an infinite number of pressure sources along the hull, but you can examine the fundamental connection between the Froude number and the oscillations in the wave resistance by just simply looking at two waves, the two dominant waves that the boat produces. And your book goes through a 4-wave example, and then of course computation takes into account attempts to take into account an infinite wave example, but the 2 waves is enough to explain the phenomena, which is really what I would like to get through to you. So the distance between where the bow wave is produced and the stern is a sink. It's a negative pressure source. So it starts off as a trough. This starts off as a crest. Now it doesn't happen right at the bow. Let me just grab a blank piece of paper. So, blank page. Boats that are fuller, I'm going to try to, here's a center line of a boat, a nice full boat. This would be like the water plane of a tanker ship. A full boat will tend to produce initial bow wave, closer to the bow, and the trough will be very close to the stern because it's very bluff. A boat that is more slender, but maybe having the same beam, like a sailboat, is going to produce a bow wave that begins further aft. So it depends highly on CP, the prismatic coefficient, which again is how much volume is pushed forward. A higher prismatic coefficient means more volume forward. A lower prismatic coefficient means less volume forward. A pointier ends. Let's go back to our lecture. So that's this K here. K tells us we have LPS, the distance between pressure sources. Again, a nomenclature I had not seen before, but that's what your book uses. The distance between pressure sources is equal to KLWL. So if it's equal to 1, we consider these waves are generated exactly at the bow and stern. If it's less than 1, they're generated somewhat after the bow and forward of the stern. So 0.8 would represent a lower prismatic boat, and 0.95 a fuller boat like the tanker I drew in the previous drawing. So these are where we assume these waves to be generated. And now we come back and look at this, and we have our wave train emanating from the bow. And again, as in the previous slide, we see that the wavelength here is fundamentally, or relative to the length of the boat, or LPS, is fundamentally linked to the Froude number. And the stern wave is generated, and its wavelength, of course, is the same, and it's fundamentally linked to the Froude number. The key is, if we think of the boat as generating these 2 wave trains, and the wave trains will give rise to a following system here, and just like in any of your work, for example, looking at drag on a wing or frictional drag, we've looked at it from the perspective of integrating the actual shear stress along the wall, but we can also look at it from a control volume perspective where we measure the change in momentum in front of and behind an object and use that to evaluate the energy that's lost, or the drag on the object. So you can evaluate energy loss to waves by just cutting a section behind the boat. And again, the Newman book in the library does this in a very interesting way, looking at a 2-dimensional boat. Not that that exists, but it's a nice way of understanding the problem. Cutting the boat section behind and looking at the flux of wave energy through that, and that can be related to energy losses due to making this wave making. So if you can reduce the wake, you have reduced your energy loss to waves. How do we reduce the wake? We can interact this bow wave and the stern wave in such a way that they cancel each other out, at least partially. So, but that will only happen under certain conditions. And let's look at those conditions. First, we'll start with greater drag, so positive interaction. How do we get positive interaction? We need a bow wave such that it's producing a trough at LPS. And those so now we have the stern wave generating a trough here and the bow wave generating a trough here. And I admit this picture is not perfect, but we have 2 waves that are in sync. And so they will add together to produce a larger wake. So how do we get a trough here? We need some integral number of wavelength. That might be 1 or 2 or 1,000. And then another half wavelength. So we need n wavelengths plus a half wavelength from the bow. relative to LPS. So here we have 2.5 lambdas in an LPS. So that's 5 halves, and therefore lambda over LPS equals 2 over 5. That's this scenario here in the upper box. If lambda over LPS equals 2.5, that means our wave is exactly such that it's interacting positively with the stern wave, and we have a larger wake. My phone is ringing. And then we have, in the bottom, we have same situation, except we have one wavelength and then a half wavelength, but it's still trough to trough. And that's the situation. We have 1.5 lambdas along LPS. Therefore, lambda is 2/3 LPS. So you have this scenario here. So we've looked at this one here as this upper one. This one is this one. Both of those are humps or peaks in the wave resistance curve. Maybe I can point those out to you while I'm here. I'm going to scoot ahead. Those would be, this one is the 2/3. This one is the 2/5. We come back here. Reduced drag. So reduced drag we're looking for the opposite scenario. We want peak to trough. We want the peak of the bow wave interacting with the trough of the stern wave. They're completely out of phase, and this will produce a cancel wave. You add these two waves together, you get nothing. How do we do that? We need some exact integral number of wavelengths in the distance LPS to get a crest exactly at the stern wave position. You can do that with two wavelengths. So 2 lambdas LPS, or lambda over LPS, is 1/2. You can do that with one wavelength exactly, such that lambda equals LPS, or lambda over LPS equals 1. And if I scoot ahead here, this is lambda over LPS equals 1. This trough here, the one in back of it, I'll put here in red, you have 2 wavelengths exactly along the boat, and you have 3 wavelengths here, and 4, and 5, and 6, and 7, 8, and 9. So now it gets infinitely numbers, so you can have an infinite number at 0 speed, but at that point your wake's not your concern anyway. So you can go through and you can determine what these humps and hollows are. So now we've seen the relationship between lambda over LPS, what critical lambda over LPSs we need for humps and hollows, and we see them here. I've recited them here: 2 2/3, 2/5, 2/7, 1 1/2, 1/3, 4th. So we went through pictorially, we looked at these particular ones, and you can draw the other ones pretty simply if you understand what's going on there. Now, what's the Froude number associated with those particular locations? Well, it depends on K, because the Froude number is always connected with the true water line length. But to get these humps and hollows, it's related to LPS, and LPS is related to the water length via K. So it's going to bring K into the equation. But we can connect Froude number with these magical ratios here that produce humps and hollows, with this inclusion of K here. So if I know, I apologize for my mail notes keep popping up, but if we include these factors in, we can compute a Froude, which I've done here: 0.535, 0.309, 0.239, 0.202, 0.378, etc., etc., etc. So you can see here these key places. I think I have in the next slide here. I do have this last hump here is known as the prismatic hump, 2/3 LPS. So I come back here, that's right around here. This is prismatic hump. Now, what this data doesn't show is that eventually, theoretically, it does return down here. Once the wavelength along the hull equals 1, there you are here. You have 1 wavelength. Now you extend it, and the drag's going to rise and rise and rise and rise until your wavelength is twice LPS, and then it actually starts to drop again. But fundamentally what happens to the ships is they don't reach, nobody powers through that to get to that theoretical portion of the curve. The stern will start to squat because you have a trough back there, and no boat can simply get out of this hole without planing or foiling, and at that point your displacement has changed and you are no longer this boat that you are evaluating. So our focus is, and I agree this is getting to be messy, our focus is really in this, oops, I did not want to do that, 1 second. Our focus is really in this regime here, looking at these humps and hollows, and again we have this is sort of the rule of thumb location, 0.4, where displacement boats are stopped. So if we look at V over root L, and again the relationship between V over root L and Froude, you can calculate pretty easily. Just be careful that the units of V over root L are knots over square root of feet, and Froude is a dimensionless number, so always use the same units. For example, meters per second and meters per second squared for gravity and meters per length. This is a connection between them. So you have a hull speed here. This is in more common naval architecture lingo, speed to length ratios. And I have some examples of these. Here's a yacht at hull speed. Land is a little bit longer than L. And you're about 1.34 for your speed to length ratio. So if you go to buy a displacement sailboat like this one, and you're trying to figure out what is its sort of maximum speed, you can do that. If you know the waterline length, L, you can calculate the maximum speed, because 1.34 is going to be your maximum speed to length ratio, roughly, and this gives you your V in knots. Now what these boats try to do is, let me go back to my little blank note here. So this is the advantage of long overhangs in a sailboat. So most sailboats look like this. It's a poorly drawn keel. But essentially here's the water line. Now often what's measured in terms of deciding how fast you should go for handicapping purposes is the water line length. But if you have these long overhangs like this and this, such that the length of the boat, the actual length overall of the boat, is much longer than the waterline length, and this is typical of more graceful classic boats. What happens when you're sailing and the boat's heeling, the effective water line, when it's heeled over, the effective water line becomes much longer. The water line might actually look like, oops, something like this. And then you have a much more effective length. So your actual wetted length goes from here to here, so it's longer than the original static wetted length that's sitting at the dock. So you increase the effective length of your boat, which allows your hull speed to be increased. And later rating rules tried to get fancier, and they tried to measure places above the water line as well as at the water line to try to keep you from just simply using long overhangs to make a longer boat than what would be measured for the ratings. To get past this point here, you have a couple options. So this is the full displacement resistance curve. It just goes up very rapidly. You can see like this. To get past this, you have boats which are what we would call semi-displacement. I think I would categorize this boat as semi-displacement. So they have used some level of hydrodynamic lift and a whole lot of horsepower to put themselves on a resistance curve that is a little bit less steep than the full displacement curve. So they're getting some of their volume out of the water through hydrodynamic lift, which puts them on a different curve. I'll put them on a dark blue curve here, which you can see is a lower slope in terms of the drag rise relative to the increase in speed. Other ships can do a better job planing, so more hydrodynamic ship. This would be like a runabout if you go on a small speedboat on a lake. Can put themselves on this curve with a much shallower slope. So the drag's continuing to rise with speed, but at a shallower slope. So an increment of horsepower actually buys you additional speed. And then finally you can bring your whole boat out of the water, and we'll be talking about this later in the semester, via foils. So the hull itself doesn't matter anymore other than the fact that it has weight, but the hull shape has zero impact because it's in the air. well, not zero impact, but has almost no impact because it's in the air. And now you're dealing with overcoming drag on the foils, which are lifting bodies. So that's induced drag and friction drag on the foils. And this, in some hydrofoils, not all, you actually go through a point like a ferry where you are pushing, you're in a steep part of the resistance curve, then it starts to foil because you're going fast enough. You need speed to create lift. And then you actually go through a regime where you have less drag. So it's a non-monotonic resistance curve due to that foiling. And you can kind of see how important it is when you have a non-monotonic curve to keep foiling, because when you unfoil, you might go from here to here in an instant. So your drag just rose 20-30%, maybe 20% in an instant is if you fall off the foils. And that's like putting on the brakes. In order to keep wave drag, there's a couple advantages. You can use very long, skinny objects like a rowing shell. Moves at a pretty high Froude number, and but is still fairly dominated by friction drag, even at a high Froude number, because it is so slender. The key to keeping waves low is making things skinny. Beam makes waves. So a skinny rowing shell or a boat sitting on multiple 2 or 3 or more skinny hulls will reduce the wave making, and that's really the advantage of cats and rowing shells in this case. So you have these fundamental trade-offs, right? A rowing shell is skinny, its wave making is low, you can reach high Froude numbers without the wave resistance becoming a large fraction of your total resistance, but the downside is stability. Something like a rowing shell is inherently unstable. If you were to take the oars away from these guys, the boat would just flip over. There's no way to stabilize that because the center of gravity is so high compared to the center of buoyancy, and there's no form stability. If it starts to lean, it's gone. There's zero stability. So they keep it stable by these oars. A catamaran obviously stays stable, produces its own form stability because you have the twin hulls. So you want to keep the beam low, the prismatic low, but all these have trade-offs because now you're reducing the amount of volume you can put in the boat, you're reducing the stability of the boat, and so as everything else, you have fundamental trade-offs. I talked about this in class, so I won't go through the bulbous bow. This is just some examples of wave-wave interaction. This is from Tuck's work, which has been taken up by his colleagues in Australia. It's a free code. I'm blanking on the name at the moment, but if you go through his webpage that I have above, you can get to it. And you can see some very interesting images he did, and Zukas and some of his colleagues. Here you have an interaction of 2 wave trains, very beautiful. It's like a Schlieren photograph, and you have he has a couple of these cool offset cases. Look, there's almost no wave making on this side. Now this would be very specific to the stagger, to the speed, and to the distance between those 2 hulls. But you can produce half wave train cancellation, and he has these penta hull vessels, these sort of 5 hull vessels, where he adjusts them to make this sort of spurious cancellation. And if you're running at the same speed all the time, there's obviously some advantage to that, but probably in a lot of these they produce more wave making at off speeds. This is an interesting paper which I put a link up to. Just a study of swimming drag. They dragged like a crash test dummy in the shape of a human. Actually, no, they didn't drag them. They put them in a water tunnel with a free surface, so an open channel, and they have a load cell here. So there's water moving this way. They're fixed relative to the laboratory, this person. And they're just measuring the drag in that position there. So it'd be like you just came off the wall. I'm not sure why they're on their back. Are they on their back or front? I can't. Yeah, they're on their back. So you just came off the wall and you're doing the backstroke. And they measure the drag. And here they have the speed, and these are typical swimming speeds. And you have the drag curve here at different depths. And so down here, these are all the deep water dummies, and you have a typical quadratic drag curve. Once they get near the surface, you have surface wave effects, and you see the drag rise that happens right here, as if you have a human hull speed. And I have to be careful because it's not clear if the wave making is really dominated by the head and the feet. You know, what is really the length between pressure sources for a human? To me, it's kind of unclear. I don't know. They used a hand to foot length. I think probably a skull to foot length may be more appropriate. I'm not sure. But you do have this large drag rise. And overall, and this goes back to our problem solving session with the submarine, you can see for a given speed, the drag rises monotonically inversely with depth, meaning towards the surface the drag is higher than is the depth. And obviously this is why the athletes try to stay below the center of the pool. Your propulsion obviously goes down as you get deeper. It's harder to actually swim in water because you are facing water resistance on the return stroke of your hands, but there's a significant hydrodynamic advantage to being away from the surface. I put some numbers in here if you want to think about swimming speeds and watts and stuff. These are just rough estimates that I have. That's about it. I want to say one more thing, which is a shallow water effect. This would be useful for one of your homework problems that I won't say which one. Everything changes when you get into shallow water, and that's the reason when we study deep and shallow water waves. The deep water waves are dispersive. Their wave speed depends on the wavelength. In shallow water, your waves are non-dispersive. The wave speed depends purely on the depth, and it's hard to operate in exactly shallow water because you have draft restrictions. But as you move towards shallow water, the depth starts to controlling the speed of the wave front, and you end up with a very different wave train. It has no transverse waves. Why does it have no transverse waves? Well, actually, let me take a step back. It can have no transverse waves. How? Because if you're going, so the wave speed is this, root GH. It's established by the depth. And you can come up with a Froude number. There are different types of Froude number. This is a depth-based Froude number. This is typically used in oceanography, where you have a velocity scale, which is the ship speed, and a wave speed scale. Here it's root GH. So this is a ratio of the ship speed to the wave speed, the speed at which waves propagate in the ocean. If you are traveling faster than the wave speed, then you outrun your transverse waves. They're back here. They're trying to move at U ship, but they can only move at root GH, and if U ship is greater than root GH, they cannot stay with you, and you have no transverse waves. You still can make divergent waves because you have the speed of propagation of this front. This can move at root GH, but it will be at an angle relative to the boat. And let me clarify that. I say it's analogous to supersonic flow, so let's have a look at that first. Oops. An object moving through space, like this, at supersonic speeds, it's producing pressure disturbances, right? Noise, for example, or the pressure disturbance of pushing air around it. So here is at time t, and it produced a pressure disturbance, and it's moving along like this at speed u. And this pressure disturbance, so here after some delta t, we're here, and this was a previous time here. So the pressure wave emanating from this source here, the previous time step has reached to here. The pressure wave here we assume is just at the body. Now you see this drawing is failing, but I will try. So these are the distance that the pressure waves have reached. So you can think of it as you're on a supersonic plane and you're just yelling from the cockpit. You open the window, which is ill-advised, and you're yelling from the cockpit, and your voice has traveled this far, and this far, and this far, and this far. So you're here, then you're here, then you're here, then you're here. So we're at this instant of time here. And at that point, the pressure, when you yelled, your voice has reached this circle right here. So the diameter of that circle is equal to, let me just clean this up a little bit. The diameter of that circle is equal to c, the sound speed, times the time, delta t. That's this length right here. These pressure waves, and there's an infinite number of them, I only drew 6 circles, have an envelope, which I was hoping would come out a little bit better, have an envelope like this. You just add in one more mini waves. Have an envelope like that. Now the distance you've traveled in the time that your pressure wave moved from here when you yelled to out here is c delta t. That distance is c delta t. The time is delta t, and in that time you have moved all the way from here to here. Make this green. It's green, and so that's this distance here, and that distance there is the speed you were traveling times the same delta t. Now this cone here, so this angle right here is a right angle. Therefore, this is a right triangle up here. The 2 blue legs and the green leg is a right triangle. The hypotenuse, I haven't said that word in a long time. The hypotenuse is the green leg, and the c delta t is the opposite angle. So we're going to focus on this angle right here. What's the angle, half angle of the cone? So we have sine phi is equal to the opposite, this space here, pardon me, the opposite, which is c delta t, divided by the hypotenuse, which is u delta t. And let's erase this, I apologize. U delta t. So we can solve for this. Now keep in mind that u over c is the Mach number. That's the ratio of the speed your vessel is moving, your airplane's moving, relative to the sound speed. That's the Mach number. And you can see that these delta t's are going to cancel out. And we solve for phi is equal to a sine, the arc sine, excuse me, of c over u, which is 1 over m, equals a sine of 1 over the Mach number. The Mach number sets up this cone right here. If your Mach number is less than 1, your voice can travel faster than the ship, so you don't have a cone. If Mach number is greater than 1, it produces a cone. If Mach number is exactly 1, your voice can travel along with you, and the angle goes to 90 degrees. Any speeds faster than that, Mach 2, Mach 3, Mach 4, the angle gets tighter and tighter and tighter because you're moving much faster relative to the sound speed. So the sound doesn't emanate very far from your plane in the time it travels, in time delta t that you're traveling along. So Mach cone tightens up. So if you look at a Mach cone, you can determine the Mach number, and if you have the Mach number, you can determine the phi of the Mach cone. This out here is a zone of silence. So if you're out here, even if you're standing right here and the airplane's going by, the airplane's gone by you, but you don't know that it's gone by you because you haven't, well, you can see it. If you have your eyes closed, you don't know it's gone by you until this pressure wave reaches you. And you can see here it's going to take a little while. The plane is going to be at least twice or 3 times the distance it's already gone before this Mach line reaches you and you hear the plane go by. So that's a delay. When you see a commercial airline go over, there is a delay, but that's only because the sound's taking a little while to reach you compared to where you see it. It's not moving supersonically, at least not at the moment. And but in this case, this is because this delay is caused by the fact that the plane is traveling faster than the sound speed. Now, a ship is the same thing in shallow water. We have c delta t. In fact, everything's the same. Absolutely everything's the same. Let me just go back to the one slide here. Here, so you have, instead of the Mach number, you have the Froude number, but it's analogous. And Mach number is a ratio of the aircraft speed to the sound speed, and the sound speed being the speed at which these waves are traveling, in this case the sound waves, that's c. The Froude number, h-base Froude number here, is the ship speed relative to root GH, which is the speed of propagation of these waves, not sound waves, but ocean waves. So they're completely analogous to the Mach cone. We'll go back here. So everything's the same. C just becomes the propagation speed of the ocean waves. U is a ship speed instead of an airplane speed. Everything's the same, except when you get to the end, RU over C is not Mach number anymore. RU over C is now the Froude number, and I will cancel out this one, and I put a Froude number here. Now in the lecture note, I was looking at a different angle here, so it was a cosine, but the cone angle is still the same. Go back to the lecture. This cone angle, which I will try to draw in here, is going to be a sine of 1 over Froude. Do a little trig, you can see those are the same thing. So how far out the waves extend and coalesce depends, that angle there, the half angle here, depends on the inverse Froude number. A higher Froude number, and this is an H-based Froude number. It's ship speed relative to root GH. It's not the Froude number we've been using, because here what's controlling the waves is not the length of the ship, it is the depth of the water. The depth of the water is controlling the wave speed. So this becomes the fundamental unit at which you would want to test ships. You need pretty shallow water or a pretty big ship. So this comes down to ferries, and this is really concerned ferries, because you can get ferries in very shallow water can produce very large waves, and there are places, even in Boston Harbor, where they've done studies of the wave wash from the ferries leading to erosion along the beaches. Often you have sheltered areas that aren't subject to large wind-driven waves, and now they're subject to periodic directional waves from ferries, which can coalesce into these fairly large structures, which once they reach the beach get even larger and can lead to erosive damage. So I think that's what I wanted to say for that lecture. Please feel comfortable with these critical concepts, identifying the transverse and divergent wave structure and the angles, and the transverse wavelength relative to the ship speed, and the transverse wavelength relative to the ship length as a function of Froude number. Actually, that was my next point here. What causes these humps and hollows? Be able to explain that in terms of bow and stern wave interaction. How long does the bow wave have to be to make a destruction or a positive interaction with the stern wave? Bulbous bows, as I discussed in the previous lecture. Approximate maximum Froude, about 0.4 is a good number to remember. And as I just discussed, how the ship wake changes in shallow water. The key thing is that in shallow water, your wave speed changes. The nature of your waves changes. They're no longer deep water waves where their speed depends on the square root of the wavelength. They're now shallow water waves where the speed depends on the square of the depth. And so they have a finite speed. It's set by the bathymetry and not by your boat. So if you are exceeding that speed, the transverse waves, which are trying to go in the same direction as you, simply can't keep up. The divergent, you have essentially what I would call a divergent set of waves emanating from the boat at an angle to the boat, because they can't keep up. Their wave faces are at an angle to your travel, and you can measure that angle, and essentially you have a cone of influence, just like you have for supersonic flight, completely analogous, except that the only differences are that you're not dealing with sound speeds, or the speed of sound being fixed by the medium. You're dealing with the speed of the ocean wave being fixed by the medium, and your characteristic non-dimensional number is not the Mach number, it's the FRH, which is the depth-based Froude number. Alright, so hopefully that is useful to you. I'll upload this now.